Welcome to another video on the AP Chem channel where we help you learn chemistry the easy way by showing you how to solve problems. Today's video is on the 2019 AP Chemistry test, and this is the fourth one in this series where we go over the solutions to the free response questions section. We have posted 3 videos, one on each of the first 3 questions, and now this final video for the 2019 AP Chem test is on questions number 4 through 7. These are the shorter questions. Every year after the AP test, they publish the questions for the FRQ section, so you can just go to the AP Chem website and download a copy of all the questions. And if you haven't done that, you should probably do that before you watch this video. But if you've got the questions already, then we are ready to check out the answers. So here is number 4, and number 4 is about a sample of CO2 gas, and originally the temperature is at 299 Kelvin, and the pressure was 0.70 atmosphere, and this is placed in a rigid container, and the temperature is then increased in the same container to 425 K. So that's the statement of the problem. So part A asks, describe the effect of raising the temperature on the motion of the CO2 molecules. So let me just draw a picture and imagine each dot represents a CO2. These are traveling at some speed. Some are faster, some are slower, so the arrows point at different directions and also have different sizes reflecting the velocity of these different CO2 molecules. When you increase the temperature, the kinetic theory of gases tells you that the velocity of these particles will in general increase, so these will be sped up compared to at a lower temperature. So what that means is the average speed of the molecule will increase as you raise the temperature. Then part B asks you to now calculate the pressure of the CO2 at the higher temperature. So of course the best way to do this is to use the ideal gas law, which is PV equals to nRT. You notice you can rearrange the ideal gas law into this form. PV over NT must be equal to R, and of course this R is the universal gas constant, so that's just a number, and so that means that this combination PV over NT is the same for every gas as long as the gas obeys the ideal gas law, and this is true for every pressure, every temperature. If you put PV NT into this particular combination, it must come out equal to R. So if you look at this problem, we are only changing the temperature. So what that means is the volume is fixed and the number of moles is fixed. And because of that, then what we can do is to just rewrite that equation as P2 over T2, because N and V are constant, and that must be equal to P1 over T1. And P2, T2 are the pressure and temperature at the end. P1, T1 are the pressure temperature at the beginning. So we can furthermore rearrange this equation and write it like that. So this is T2 divided by T1. And now you can put the numbers in. P1 is equal to 0.70. I'm just going to skip the units because at the end the pressure will come out in units of atmospheres. T2 is 425, and T1 is 299. So if you put all of that in, you will get P2 equals to 0.99, and again the units are atmospheres. So part C, from B we can see that the pressure goes up as a function of temperature. So part C asks, why does the pressure go up, and explain in terms of the kinetic theory of gas. So obviously we have said that at higher temperature the gas travels faster. The pressure is created by the collision of the gas with the walls. So these walls are suffering collisions with the gas particles. So as the gas particles are traveling faster, the pressure that is being exerted on the walls from the gas particles are also increasing. So as temperature goes up, the speed goes up, as we have said in part A, and as a result of that, the pressure goes up because of the higher forces, increased forces from the collisions of the CO2 with the walls. Sorry, that's a long sentence. So finally, part D, it says the observation was the pressure that you get after you raised the temperature was lower than what was expected from the ideal gas law. So the question is, why is that? Well, that's a reflection of the fact that there is non-ideal behavior in the gas, and the ideal gas law assumes that the particles do not attract or repel each other, and that is obviously not true. There are intermolecular interactions between the CO2 molecules, so they do actually have some weak attractive interaction, and so in general the actual observed pressure is lower than the ideal pressure because they kind of stick a little together. So the next one is number 5. I've reproduced that spectrum here because I don't want to draw it, otherwise I would probably have got it wrong. So the part A of the question says, based on this photoelectron spectrum, what is the ground state electronic configuration of this element? This is a fairly idealized photoelectron spectrum. I've never really seen one like that. But supposedly what happens is that you can irradiate an atom with light. If the light is commensurate with the energy of the electron in its orbital, it would eject that electron. So you're really counting electrons based on sort of the energy it takes to eject them. So essentially these are reflecting the energies of the electrons, and of course the height on this y-axis, they're also reflecting the number of electrons that are actually coming out. So you see there is clearly a shell structure, and if you then think about that, then this must be representing the 1s, 2s, 2p, so this is n equals to 2, n equals to 1, and so these are the n equals to 3, and this would be the n equals to 4 shell, right? So obviously this is commensurate with what you would expect to be the shell structure of the atom. So this would be 1s, and that's about 2 electrons. So this is 2, but that height is about 6 electrons. So this is expected to be 1s2, 2s2, 2p6, 3s2, 3p6, and there are 2 in the 4s, so 4s2. And that is part 1. So part 2 in part A asks you to identify that element. So you can just look up the periodic table and the element that has that particular electronic configuration is calcium. So part B asks you to calculate the wavelength in meters of the radiation that is needed to remove an electron from the valence shell. So clearly the valence shell are the 4s. So what you are trying to do is to eject an electron from there, and you see there's a certain energy that is required for the photon to be able to remove a 4s electron. So the question is, what is the wavelength of that photon that is required? So the relationship between the energy and the frequency of the photon is E equals to h nu. And this equation is actually on the equation page, so you don't have to memorize this. The constant here, this h, is called the Planck's constant, and the nu in this case is the frequency of the photon, of the light associated with that photon. There is another relationship in the equation on the equation page, which relates then the frequency with the wavelength, because part B asks you to calculate the wavelength. And then the wavelength and the frequency is related to each other by the speed of light. And that is the speed of light, c, is equal to lambda, the wavelength, times nu, the frequency. So let me write down what these are. So this is now the wavelength, and nu is of course the frequency. C, of course, is the speed of light. So what you can do is to put all of these back together. What you can first do is to rewrite nu is equal to c over lambda, and then you can put that into this equation. So clearly you see that E is equal to hc over lambda. So this is one equation relating E to lambda, or you can reverse that and write lambda is equal to hc over E. And now you can put the numbers in. The equation page gives you the values for the Planck constant and the speed of light. So the Planck constant is 6.626 times 10 to the minus 34 joules second, and the speed of light is 3.0. I'm trying to pick the right color. 3.00 times 10 to the minus times 10 to the 8 meters per second. And so now if you put that in, you should be able to calculate the wavelength. So 6.626 times 10 to the minus 34. I'm going to omit the units because at the end the wavelength will come out in SI unit for length, which is in meters. This is multiplied by 3.00 times 10 to the 8. And that is all divided by the energy here. So that is 0.980 times 10 to the minus 18. So you can put all that in and calculate the value for lambda, and that turns out to be equal to 2.03 times 10 to the minus 7. And putting the units back in, SI unit for length is meters. Number 6, this one is about the decomposition of NO2, and it gives you 2NO plus 1O2. These are all gases. So let's get to the question. I've reproduced some of the data because I know if I were to draw them, I would probably get them messed up. So the first one is explain how these graphs indicate that the reaction is second order. So these are time course data for the concentration of the NO2 as a function of time plotted in three different ways. These are the same data, but you see for the first one is the concentration of NO2. The second one is 1 over the concentration of NO2. And for the third one is the logarithm of the concentration of NO2. And so the equation page gives you some of these integrated rate law for first and second order reactions. So let me just remind you very quickly for first order reactions, if you plot log of the reactant, I'll just call that x as a function of time, you will see that it is equal to log of the initial minus kt. So if the reaction was first order, then the plot of log of the reactant concentration as a function of time would have produced a straight line. So you see this isn't straight, so we know it's not first order. On the other hand, if it was second order, then if you plot 1 over the concentration of the reactant as a function of time, it would follow this equation. Again, K is the rate constant. So in this case, 1 over the concentration would have produced a straight line. So you see, this is the plot right there. And then indeed, that looks pretty straight. So what we can see from that plot is that this reaction must be a second order, because that plot gives you a straight line. So part B asks you to write down the rate expression for that. So once you know this is a second order reaction, it's fairly straightforward, because then you can simply write down the rate law. Rate must be equal to K multiplied by the reactant concentration to the second power. And now part C has to do with these two mechanisms. So I've reproduced them right here, and is asking you for each of these mechanisms whether this is consistent with the observed data. Well, first of all, the mechanism must have an overall reaction that matches the reaction that you are studying. Otherwise, the mechanism is wrong in the first place. You can verify, in fact, that these two actually do give you the correct overall reaction. So now we can take a look at each of them and try to see if they match this second order behavior that's observed experimentally. So let's take a look at the first one. So you see in the first one, the slow step is the rate determining step. So the rate of the overall reaction is controlled by the slow step. And in the slow step, the reaction is bimolecular, because it requires the collision of two NO2 molecules in order to give you product. So the rate law for mechanism 1 is the rate should be some rate constant multiplied by the NO2 concentration squared. So what that means is that that mechanism is in fact consistent with the observed rate law, because we expect it to be a second order reaction. And now for mechanism 2, which is a little more complicated, the slow step in that mechanism is the second step. So in this case, the second step only really have one reactant. So you see it's N2O4 only. However, that N2O4 is not part of the reaction. So you see in this reaction, in the overall reaction, there is no N2O4. But you see N2O4 is created by the first step in mechanism 2, and then in the second step is used up again. So in these cases, in those cases, this N2O4 is called an intermediate of the reaction. It's created by some early step and then destroyed by some later step in the mechanism, so it doesn't really show up in the overall reaction. So based on the second step, which is the slow step, then you would expect the overall rate of the reaction to be to depend on the N2O4 concentration to only the first power, because that is a unimolecular reaction. However, you see that step 1 is a fast equilibrium. So step 1 right there, it says fast equilibrium. So what that means is that the N2O4 concentration that is in the reaction is established by an equilibrium that is achieved in the first step. So you see the equilibrium is basically taking 2 NO2 and making 1 N2O4. So clearly, if you write down the equilibrium expression for that step, you see that the N2O4 concentration divided by the NO2 concentration squared should be equal to the equilibrium constant. So what that implies is that, in fact, this N2O4 concentration that shows up in the rate law can be rewritten in terms of the NO2 concentration. So if you take this and you move it up to this side, then you have an expression for N2O4. So the N2O4 could be rewritten as the equilibrium constant. Let me just write KEQ in case there is any confusion about that K versus the K in the rate laws. So you can rewrite that. So clearly at the end, instead of writing the rate as a function of N2O4, you can rewrite it as a function of the square of NO2. And so you see again that is in fact consistent with the second order rate law that we have observed. So that also is consistent with the observed kinetics. Now number 7. Let me write down the chemical equation first before I start talking about the problem. So the balanced equation is 6H plus 2MnO4 minus plus 5H2C2O4 going to 10CO2 plus 8H2O plus 2Mn2 plus. So that is the balanced equation. So the problem says a student takes a 0.139 gram sample of oxalic acid. So oxalic acid is this guy. And titrate it using potassium permanganate. So potassium permanganate is this permanganate with the K plus ion in the solution. The permanganate has a purple color. So when this reaction occurs and there's still oxalic acid in the container, in the flask, you won't see the purple color because the permanganate is being destroyed. But as you reach the endpoint of the titration and used up all the oxalic acid, then you begin to see the purple color of the potassium permanganate, and that would indicate the endpoint of the titration. So question A asks you to identify which species is reduced in the titration reaction. So to do that, you need to work out the oxidation states of all of the elements in each compound. The rule for oxidation states is if H appears in the compound, then it would have a +1 oxidation state unless it's in H2. If O appears in a compound, it would have oxidation state equal to -2 for every O atom unless it is in O2. And then all of the compounds, when you add up all the oxidation states, must equal to the total charge of the compound. So I'm just going to go through and work out all of the oxidation states of everything, because that is a good exercise anyway. So this one right there has an H in an ion by itself, which has a charge of +1. So this H has a +1 oxidation state. In the MnO4 minus, you notice the overall charge is a -1. Each O, as we have said, is a -2, but there are 4 of them, so the total is -8. In order to have an overall minus, then we see that the Mn must be a +7. And for the oxalic acid, the 2H, each one is +1, will give you a +2 together. These 4 O's, just like in the 4 O's in the permanganate, would give you a -8. The overall charge of that compound is 0. So what that means is that these 2 carbons together must be a +6. And so each carbon individually is +3. So I'm not going to write that down because that has nothing to do with this problem. So you can go and do that for everything on the right side. I'm just going to write down the oxidation state of things that are not H or O, because H or O, the oxidation states are fixed already. So this carbon is +4. And then clearly this manganese ion has an overall charge of +2. So this is a +2 oxidation state. So what you can see is that during this reaction, the species that is reduced is the manganese, because originally its oxidation state was +7. At the end of the reaction, the manganese, which is right there, has an oxidation state that is lower. So in this case, the permanganate is the species that is being reduced. So just again about the terminology, reduced means that the oxidation state has come down. So in this case, going from 7 to 4, Mn is reduced. So part B asks you to look at that diagram and try to figure out what is the volume of the titrant that is needed to get to the endpoint. So in this case, for part B, I've reproduced that picture right there. So we have to look at the 2 readings at the beginning and at the end of the titration. Obviously, at the beginning, the level is higher, so you have to go there and read it. So generally, what you do is that there's a meniscus for the liquid, and you read the volume at the bottom. So let me see if I can put a line through that. So that's basically where you're supposed to read the volume. I'm going to erase the line so we can actually look at what that is. But looking at the bottom of the curvature, you see this is a 3 right there. This is a 4. So you count 1, 2, 3. So it's a little lower than 3. So I would call that maybe 3.35. And now at the end of the titration, you look at that. And now you see this is 29, this is 30, so this is 0.1, 0.2, 0.3, 0.4, a little lower than 0.5. So I would say maybe 39.55. So these are the initial and final volume. So what you need to do is to, 29, not 39. So what you can then do is to look at the volume by subtracting those from each other. Let me use a different color. 29.55 minus 3.35. It's in units of milliliters, so that's 26.20. And so now part C ask you to take that volume and the concentration for the KMNO4, it tells you is 0.0235 molar, and then is asking you to calculate the number of moles of the KMnO4 that's needed to neutralize the oxalic acid. So that's just multiplying the concentration by the volume reading that we just took. So the number of moles of MnO4 minus must be equal to the concentration multiplied by the volume, but we will write that in liters because molar is mole over liters. So 26.20 divided by 1,000, and that's in units of liters. So if you do that, the number of moles come out to be 0.000616 moles. So this should have three significant figures. The reason is because the concentration of the MnO4 of the KMnO4 solution only has three significant figures. And so finally, part D asks you, what if the student wanted to use a KMnO4 solution at a concentration of 0.00143 molar? Well, in principle, the titration would still work, but of course you can use the new concentration to calculate how much volume would be needed in order to get to the endpoint. So you see, this number right here is more than 10 times less than this concentration right there. So what that means is, if you were to titrate the same amount of oxalic acid, you would have needed a volume that's more than 10 times as much as you have found in this first experiment. And so in the first experiment, you used 26.2. So if you had used this KMnO4 concentration, you would have needed more than 10 times, which is more than 260 mils of the solution. And so that would not work because you see the burette in this case only holds 50, right? So 0 to 50. And so in this case, one burette full of the solution will not get you there. So the concentration here is too dilute. So I'll just say no, too dilute. Okay, so that is the end of the solutions to questions 4 through 7 in the 2019 AP Chem FRQ questions section. And if you are looking for more content to help you prepare for your AP Chem test, we have a lot more resources on our channel. So please do subscribe to our channel so that when these new materials are available, you can get the notification right away.